Now we'll go for the time expansion in time scaling. Okay, so I'm explaining about I'm explaining you about time scaling operation. So in that, the time scaling operation on a signal x of t, and signal x of t can be expressed as x of small a into t. If the value of that small a, that is mod a, is greater than 1, then we go for the time compression. I explained you already. Now if that mod of a value is less than 1, then we get time expansion. Okay, so now we'll explain the time expansion of time scaling operation. Simple. I will take the same examples of what I had taken for time compression. So how the waveforms will change for time expansion. I hope you already have an idea. There the time has been compressed by scaling factor A. Here also the time signal will be expanded by the same scaling factor A. So you will get a better idea if you observe the waveforms. Now first I have to consider signal x of t. So say I am considering signal x of t like this. First example that I had taken t x of t 0 1 2 1 2. See this one. This is my example. Now I have to perform the scaling operation x of at. Here for time expansion, I have to consider the modulus of a value should be less than 1. Modulus of a means that is minus also becomes plus, that is like the values of 0 0.2, 0 0.4, 0 0.5, 0 0.9, whatever it may be. 0 to 1, you have to take the values between 0 to 1. So for that I have taken the value as 0 0.5. I will take the value as 0 0.5. So here let's consider the small a value equal to 0 0.5, which is nothing but 1 by 2. So our time scaled expression for x of t will be written as x of 0.5 t, which is nothing but x of 1 by 2 into t. Now I will need the signal for this time scaled signal x of 1 by 2 into t, x of 1 by 2 into t. So for this I need the waveform. So how can you draw this one? Simple. For this I am drawing like this. So take this as t, and here I have to need x of 1 by 2 into t. How can you get? So the procedure is same. So there in time expansion, there is also one of the operation of time scaling. There what I did, I divided the every time instant. By the scaling factor a. Here also you have to divide the every time instant with the scaling factor a. There the value of a is 2. Here the value of a is 1 by 2. That means you have to divide this value, that is the first time instant 0, by 1 by 2. This is also by 1 by 2. This is also by 1 by 2. Divide every instant by 1 by 2. Okay. Now 1 by 2 into 0. What happens? 1 by 2 goes upside. 2 into 0, that is 0, goes upside. So 0 by anything is 0. 0 by anything is 0. So here the amplitude is 2. For the next case, 1 by 1 by 2. 1 by 1 by 2. That means 2 goes upside. That's 2 into 1. 2 into 1 is 2. 2 into 1 is 2. See, this is 1. This is 2. This is 2. This is 3. And this is 4. Let us take, so for this, 1 divided by 1 by 2. Or simply you can write 1 by 0.5. 1 by 0.5 is 2, or 1 divided by 1 by 2. If the 2 goes upside, that value will be equal to 2 into 1, 2. So at 2, the amplitude is 2 because here also there is no change in amplitude. Only the change is with respect to the time. Only the change is with respect to the time. Only the change is with respect to time. Now see, here there is 2 and the amplitude is 2. So far here also the amplitude is 2 up to now. Next, 2 by 1 by 2. So if 1 by 2, these 2 goes outside, 2 into 2. 2 into 2, that is 4, or simply 2 by 0 0.5. 2 by 0 0.5 is also equal to 4. Okay, is equal to 4. So this is 4. The amplitude is 2. So here also the amplitude is 2. That means this one. This one. See, the waveform has like this. This is the given signal x of t, and this is x of 1 by 2 into t, or x of 0 0.5 into t. Both are same. So here the a value is less than, a value is less than 1. For that I had taken value as 0 0.5. So see, here the signal is expanded with respect to time, expanded by the factor of a. Here the a value is 1 by 2. So this is expanded. Okay, simple. This is expanded. Now next thing, if you, for your better understanding, I will go for 2 more examples. The same example what that there I had taken for time compression. See, so it is expanded. Now the signal I had taken like this: minus 0, 1, 2, minus 1, minus 2, 1, 2. Clear? Now see, yeah, this is my input signal. This is the t and this is x of t. Now what I need? T x of 0 0.5 t or x of 1 by 2 into t. Both are same. I need these ones. Simple, it will be expanded. Okay, just by the variation of the scaling factor. Dependent on the scaling factor, it will be expanded. Dependent on the value of the scaling factor. Here the scaling factor is less than 1. So that is 1 by 2. So it will be expanded based on this scaling factor. Now the pressure is same. Now I have to divide. Each time instant by the scaling factor. So this divide by, so here I had written 1 by 2, so here I will write 0 0.5. Both are same. 0 0.5, 0 0.5, 0, 0 0.5, 0 0.5, 0 0.5. You don't need to write this. For your understanding, I am writing there. Okay. Now minus 2 by 0 0.5, or minus 2 by 1 by 2 goes offset, that is minus 4. So 1, minus 1, minus 2, minus 3, minus 4. Think minus 4. So here also 1, 2, 3, 4. So for this there is minus 4. So for the minus 4, the value is 2. 1, 2. 5 plus 4, the value is 2. Clear? Next, minus 1 by 0 0.5. Minus 1 by 0 0.5. What is the value of minus 1 by 0 0.5? So simply, that is minus 2. So this value. Here also the value is 2. Next, 0 by 0 0.5. 0 by anything is 0. At 0, the value is 2. Next, 1 by 0 0.5. 1 by 0 0.5 is nothing but 2. So at 2, the amplitude is 2. Next, 2 by 0 0.5. 2 by 0 0.5 is nothing but 4. At 4 also the amplitude is 2. Because this is time scaling. So the variation is with respect to time. There is no change in amplitude. Hence the waveform is like this. 4. Clear? See, the signal is expanded. This is a time expansion. The time expansion is based on the scaling factor. With respect to the scaling factor, the time is expanded, the signal time is expanded. So this is time expansion of the signal. Clear? So these are the two examples. So you can go for another example also if you wish to continue. So I already explained. I hope this is very clear for you. This is very clear for you. There is no need to go for other example. So you can practice more examples. Okay. Simple. We will have to divide every time instant with that factor, scaling factor, whatever they had given. So for that I had taken the example as 0.5. Okay. Now remember, I remember one thing. This time scaling will give result in either time expansion or time compression based on the scaling factor A. Here I taken as A, you can take anything. So you can take alpha, whatever it may be. Okay. Generally this A value is always positive. Okay. Generally the A value is positive. Okay. So for that, for time compression I had given 3 examples, and for time expansion I had 2 examples. So you can clear with this time scaling. Your work is to perform the time scaling operation with respect to discrete time signal, x of n, with respect to discrete time signal x of n. So consider a discrete time signal x of n like this, x of n 0, this is n, so this is 1, this is 2, 0 minus 1, this is also 2. Okay, or you can like this 2, this is 3, minus 2, 3. There is a signal x of n, the signal like this x of n. Now you have to perform the time scaling operation on this. So you have to draw the waveforms of x of 2n and x of 0.5 and x of 2n and x of 0.5n. The logic is same. So here also you have to divide with this one. So divide with 0.5 for this one and divide with 2 for this one each instant. That is, for this what will you do? You will divide this minus 2 with 2, minus 2 with 2, 2, 2, 2, 2. Simple. So how will you get the answer? How will you get the answer? How will you get the answer? Simple. Minus 2 by 2. Minus 2 by 2. That is minus 1. So we will get minus 1. And minus 1 by 2. Minus 1 by 2 is, yeah, come to this one. Minus 1 by 2 is, minus 1 by 2 is minus 0.5. Minus 0.5. Next one is 0 by 2. 0. 1 by 2. 0.5. 2 by 2. 1. 2 by 2. 1. See, for discrete time signals, we have the values only for integer values of n. That is for n equal to 1, n equal to 2, n equal to 3, or n equal to minus 1, n equal to minus 2, n equal to minus 3. For those values only you have the x of n. For n equal to 1.5, 1 equal to 2.5, or n equal to 1.9, for those values you don't have x of n. In discrete time signals, we have the values of x of n only for n equal to 1, 2, 3, 4, so on, or 0, or minus 1, minus 2, minus 3. For that reason, here for this minus 0.5 and plus 0.5, there is no point. So for discrete time signals, the x of n value does not have the values for n equal to 2.5, 2.9, 1.5, 1.1. If there is any points, fractions, then x of n does not exist. X of n exists only for n equal to 1, 2, 3, 0, minus 1, minus 2. For that reason, so this minus 0.5, there will be no signal. There will be no signal. And plus 0.5 also there will be no signal. That is 0. X of n is 0. So how the waveform will be? At 1, for this at 1 the amplitude is 3. At 1 that is 3. Here we don't get any output. Leave it. For 0 it is 1. For 0 it is 1. For this 0.5 we don't get any output. For 1, so there, for this there is nothing. For this also there is nothing. For 0 we have 1. Next for 1 is 0.5. We don't get anything. The last one is 1. For 1 we have 3. So this is the waveform for x of 2n. So in the same way, you have to draw the waveform for x of 0.5n, x of 0.5n, or x of 1 by 2n, 1 by 2n. So clearly understand the concept, then this is very easy to draw the waveform. So we can easily draw the waveform for x of 0.5n. So this is the just explanation of time scaling with respect to discrete time signal x of n, with respect to discrete time signal x of n. Why I explain this means here there is a point of this one, here we don't get the values. For that reason I explained this. So we will do this at your home, that is for your practice. Okay, I explained time scaling. So in time scaling you have time expansion and time compression. First I explained time compression and then I explained time expansion. So in these operations on signals we have left with only two things, that is amplitude scaling and time reversal. Next I will go for the amplitude scaling. Now we will see amplitude scaling operation. Before this, I explain you time scaling. So time compression and time expansion, okay, everything I explained you. So now I will explain the operation amplitude scaling. So here the signal is scaled with respect to amplitude. That is, there is a change in amplitude and there will be no change with respect to time. With respect to time, there will be no change. Only the change will be with respect to amplitude. That is, amplitude will be scaled in amplitude scaling. Now, to explain the amplitude scaling operation and considering the signal x of t, let us consider a continuous time signal as x of t. Now, if I perform amplitude scaling operation on this x of t, it will produce an output y of t that will be equal to some constant. So here I am taking the constant as a into x of t. So in time scaling I have taken a constant as small a. Just for variation, here I have taken the constant as capital A. Okay, you can take anything. You can take a beta, whatever it may be. Okay. Now, see the difference for time scaling and amplitude scaling is there. The small a constant is multiplied to the t inside of x of that one. So inside x there is t. Now in time scaling, that a is multiplied to the time. Okay. Hence there is a change with respect to time. That is, time will be scaled because there we will write like x of 80 in time scaling. In time scaling we will write like x of 80. There that a is multiplied to the t, which is inside x. Means the time will be scaled. But here see, come to amplitude scaling. Here the constant is multiplied to the complete signal, the x of t. That is, the complete signal will be multiplied with constant a. That is, here the amplitude of the signal will be multiplied by this constant. Simply. So simply the amplitude scaling operation of if you perform amplitude scaling operation on a signal x of t, then it will produce output like a into x of t. Now the output y of t. Y of t is nothing but 8x of t. The output of the signal x of t, where we perform amplitude scaling, is nothing but the, here at every instant of time, the amplitude of signal will be multiplied with a at that instant. Okay, simple. Now I will explain this with the help of diagram, as I explained for the previous cases. So I explained for time scaling, time shifting, amplitude, everything with respect to diagrams. So here also I will explain this concept with the help of diagrams. Okay. Now, so this is the amplitude scaling function, a into x of t. Now, in time scaling, we have a time compression and time expansion. In the same way, here also in amplitude scaling, we have amplification and attenuation. Okay, their time compression and time expansion is dependent on the value of small a. Here I take capital A. So the amplification or the attenuation will be dependent on the value of capital A. Simply, what to say in a simple manner, if I want to say it in a simple manner, if mod of A value, mod of A magnitude, that is, so generally this value will be positive, we treat that value as a positive. Okay, mod of A value is greater than 1, okay, then the signal will be increased or amplified. That is nothing but amplification. So it is, if mod A is greater than 1, then it is said to be amplified. That is amplification. Okay, if that signal is increased. Simple. Here I will take the amplitude on y-axis. So the amplitude of the signal will be increased. So there is a change in with respect to y-axis. That is, the amplitude of the signal will be increased. On the time axis, that is, the time of the signal does not change. There is no change with respect to time, because we are performing amplitude scaling operation. So if mod of A is greater than 1, then the signal will be increased along y-axis, that is in the positive x direction, or in both ways, positive and negative, that is along y-axis, positive and negative. The signal will be increased, hence it is called as amplification. Okay. Now, if mod A is less than 1, that is, the value is between 0 to 1, so you can take 0.5, 0.9, or value is between 0 to 1, because it is mod A, so the values are 0 to 1. If you take any value between 0 to 1, then the signal will be reduced along the y-axis, that is both in positive and negative direction, that is reduced along the y-axis, hence that is nothing but reduction, or we can call it as this attenuation or reduction. So the reduction of the signal is nothing but attenuation. Okay, so if the value of capital A is greater than 1, then we can call it as an amplification. If the value of mod A is less than 1, then we call it as an attenuation. Okay, so these are the explanation with respect to this amplitude scaling. Okay, simple. So if I want to explain this graphically, I have to take the signal x of t. So I have to consider an example for a signal x of t. So let us consider the signal x of t like this. The signal x of t like this. One, two. Okay. So this is t and this is x of t. Okay. Now I have to perform the amplitude scaling operation. That is, it should be scaled with respect to the amplitude, the scaling of amplitude. So here I have taken the amplitude on y-axis. So there is a change in y-axis and there is no change with respect to time. Now in that there are two cases. The first one is mod A is greater than 1 and next one is mod A is less than 1. First I will consider for first condition, that is mod A is greater than 1. That is, here I will take the value of capital A as 2. As 2. Now 2 is greater than 1. Okay, that is mod A is greater than 1. So it is satisfying this one. So what I said, if mod A is greater than 1, then the signal should be increased in y-axis. That is, it should be amplified. Nothing but amplification. Okay, how it will happen? See, now the amplitude scale version for A equal to 2 is y of t equal to A into x of t. That is 2 into x of t. Actually, this is x of t. Now we go for 2 into x of t. Okay, so how will you draw that one? 2 into x of t. This is t, and this is 2 into x of t. 2 into x of t. So I will take this as 2 into x of t on y axis. Now, is there any change in time? There will be no change in time. So, if I write this in an equation format, how will you write the equation format for the input signal? For the input signal, if you want to write an equation format, let us consider like this. X of t equal to 0 for t less than 0, 2 for 0 less than or equal to t less than or equal to 2, and 0 t greater than 0. Simple. T less than 0, x of t is 0. Between 0 and 2, x of t is 2, and greater than 2, x of t is 0. Now, I have to write for y of t, which is nothing but 2 into x of t. That is amplitude scaling for mod A greater than 1. So here I take an A value as 2. So the signal is 2 into x of t. So for this I have to write diagram. Same 1, 2, 1. As I said, it will be increased in y direction. Okay. How it will increase? Simple. For t less than 0, x of t is 0. X of t is 0. So put here x of, so t less than 0. T less than 0. Put here x of t. This is the t. Less than 0 is this one. In this case, the x of t value is 0. What is the value of 2 into x of t? Now, 2 into x of t equal to 0 for t less than 0. Because 0 into 2. 2 into 0. 2 into 0 is 0. So there is no signal. Now between 0 less than or equal to t less than or equal to 2. Between 0 less than or equal to t less than or equal to 2. X of t is 2. So substitute 2 here. So 2 into 2. 4. 2 into 2. 4. So the value of 2 into x of t. 2 into x of t between 0 and 2. Between 0 and 2 is 4. So here the value is 4. Okay. Now t greater than 2. The last one, t greater than 2. T greater than 2. Now x of t is 0. So substitute 0 here. 2 into 0. 0. Okay. So greater than 2 it is also 0. That means this is consider this. Okay. Simple. See, here the signal is this one. Now the signal is expanded in y-axis. The signal is expanded in y-axis. Okay. So as it is expanded, increased, amplified, hence it is nothing but amplification. It is amplification. Okay. Or you can take x of t equal to 2 sin t. It is a signal 2 sin t. Then amplitude scaling of this one is 2 into x of t. If capital A equal to 2 into x of t, what happens? 2 into 2, 4 sin t. 4 sin t. So you can take sin t or sin omega t. 2 sin omega t. Then this equation will be 4 sin omega t, 4 sine omega t. So if you want to represent like an equation, so this is a representation for amplitude scaling if mod A is greater than 1, that is the value, the constant value is greater than 1. Or you can represent it in diagrammatic form also. Okay, you can draw the sine waves. Okay, you can draw the sine waves, and the amplitude of sine wave will be increased. Remember, there is no change in the shape. Here the shape is only like this. It will be increased. It will be increased. So in the same way, if you consider a sine wave, the same way, if you take a sine wave, take a sine wave as x of t, this is t. Now t, 2x of t, 2x of t, let's consider this as 1 plus 1 and this as minus 1. Now that will be multiplied with 2. So what happens? So this will be increased. This will be increased. So this is plus 2 minus 1 minus 2. So this is for 2x of t. So we can represent like this also. Okay, if there is a sine wave, so if I want to perform amplitude scaling, so in this way I can perform the amplitude scaling. In this way I can write an equation formulas. So in this way also. So there is no need to do like this every time. Just multiply with that factor. Here the factor is 2. So actually this is 2. So 2 into 2, 4. So it should be increased to 4. Okay. Just the output y of t amplitude is a times, that is the constant, a times the amplitude of the signal at that instant. So remember, now the y of t signal output is a times the amplitude of the signal x of t at that instant. So at particular instant, the amplitude of x of t is 3 and the a value is 2. So at that instant, that 3 will be multiplied with this 2. 3 into 2, 6. So at that instant, the amplitude is 6. So it is increased twice, double, 2 times. So 3 into 2, 6. Clear? So this is the explanation if the value of a is greater than 1. The same way, if the value of a is less than 1, the value of a is less than 1. So there is no need to write all this. A is less than 1. That is, you have to consider the value between 0 to 1. So 0 0.2, 0 0.3, 0 0.5. So I am taking the value as 0 0.5. So which is nothing but 1 by 2. So if in the second case, if a equal to 0.5, which is nothing but 1 by 2. So whose value is less than 1? Here the value is less than 1. Now the signal will be decreased in y-axis, reduced, hence reduction takes place. It is nothing but attenuation. How will it happen? Simple. So same signal, if you consider the same signal, so this is the same signal. Now for the signal, the input signal is like this. T, x of t, this is 1, this is 2, 1, 2, see, this is the signal. Okay, this is the signal. Now for this signal, I have to perform the amplitude scaling for mod A less than 1. So here I have taken A as 1 by 2. So here y of t equal to A, that is 1 by 2 into x of t. Now I have to write the signal for this 1 by 2 into x of t. How will you write? Simple logic. So t, this is 1 by 2 into x of t. This is 1 by 2 into x of t. Okay. Now, see, his amplitude is 2. So multiply the amplitude with 1 by 2. So 2 into 1 by 2 or 1 by 2 into 2. Simply 1 by 2 into 2. 2 gets cancelled, that will be given as 1. So the amplitude of the signal will be equal to 1. Amplitude of the signal will be equal to 1 at 0, at 1, at 2. And in the remaining cases, and all the remaining cases, the value is 0. So 0 into anything, 0 into anything is 0. So here there will be no signal. See, 1, 2. This is 1 and this is 2. So less than 0, x of t is 0. So 1 by 2, anything into 0 is 0. There will be no signal because there is no change in time. The time is fixed. Only the change in amplitude. So at 0, here the amplitude is 2. So 1 by 2 into 2, that is 1. That is 1 here. And at 1 also, the amplitude is 2 for x of t. So here for 1 by 2 into 2, it gets equal to 1. So this is also for 1. At 2 also, the amplitude is 2 for x of t. I need for y of t. Y of t is 1 by 2 into x of t. 1 by 2 into 2. That is again 1. Okay. So simply we can write like this. See, here the amplitude of signal is reduced, decreased, that is reduction. Hence it is nothing but attenuation. It is attenuation. Okay. So if you observe the diagrams, so here the change is with respect to the y-axis. The signal is increased in y-axis. That is, the scaling has taken place with respect to amplitude. Hence it is called as amplification. In this case, the change is taken with respect to y-axis, but it is reduced. Decreased. Reduction takes place. Hence it is nothing but attenuation. That is, the scaling is with respect to amplitude, but it is reduced. Hence it is nothing but attenuation, reduction. Okay. So this is the concepts. If you want to take other examples, here also, if you want to take this example, x of t equal to some 6 sine omega t. Okay, I can write it. And the factor a is 1 by 2. A is 1 by 2 or a equal to 1 by 3. You can take 1 by 3. 1 by 3, anything. Now, amplitude scaling version, that is y of t, which is equal to 1 by 3 into x of t. So I have to multiply the amplitude of the signal with the constant. The constant is 1 by 3. So 1 by 3 into 6. So 1 by 3 into 6 is 6 by 3. Then nothing but 2. 2 sine omega t. So 2 sine omega t. So in this way also you can write. Or you can represent with the help of a diagram also. Here the 1 is increased 2. If I go for 1 by 2 into x of t, for this signal, if I go for 1 by 2 into, what happens? The amplitude will be reduced. That is, it will become for 0.5. Because 1 by 2 into 1 by 2 into 1 is 0.5. Okay, 0.5. So for this signal, if we want to write amplitude scaling, if a is less than 1, that if a equal to 1 by 2, for this signal, if a equal to 1 by 2, if I want to write like this, for this signal, simple. So because this side is 0.5, this is minus 0.5. Okay, t 1 by 2 into x of t, 1 by 2 into x of t. So this is regarding amplitude scaling. So in amplitude scaling we will get two things, that is amplification and attenuation. So all these are with respect to continuous time signal. Now the amplitude scaling operation can be done on discrete time variable also. So that is for your practice. So you have to practice the amplitude scaling operation with respect to discrete time variable n. That is, you have to consider a signal as x of n. Like this. At 0, 1, the value is 1. At 1, the value is 2. At minus 1 also the value is 2. That is n, and this is x of n. So consider a signal like this. Now, if there we have to consider the signal as amplitude scaling of this version, y of n, and y of n will be equal to some constant. Here I have taken capital A, you can take small a or whatever. and you can take capital D, whatever it may be. So here I have taken small a. If mod of small a is greater than 1, then it will go for amplification. If mod of small a is less than 1, then it will go for attenuation. The concept is same for continuous time signal and discrete time. Here the continuous time variable t will be here, and there we have the discrete time variable n. Only that is the only change. So y of n equal to a into x of n. Let a equal to 2. A equal to 2. Now this is x of n. I need 2 into x of n. How can I get? So n, it is n at every instant at -1 the signal amplitude is 2. So that should be multiplied with the constant. Here the constant is 2. So 2 into 2, that is 4. So at -1 the amplitude will be 4. At 0 the amplitude is 1. At 0 instant the amplitude is 1. So what we will do? I have to multiply that 1 with the constant 2. 2 into 1, 2. So this is 2, this is 4. Again at 1, the amplitude of x of n is 2. The constant is 2. So you have to multiply this 2 into 2, that is 4. This is 4. Simple. So 2, 1, 2. 4 to 2, that is, it is increased by the factor a times. Okay. So if a is 5, so this signal should be multiplied with 5. 5 into 2, 10. 5 into 1, 5. 5 into 2, 10. 10, 5, 10. There is no change with respect to n because it is amplitude scaling. Whenever we perform amplitude scaling, the change is with respect to amplitude only. There will be no change with respect to the time. That is, here the discrete time variable is n. There is no change with respect to n. So I had gone for the outlines of this amplitude scaling with respect to discrete time variable. So you can practice with more examples. So I have shown you for a greater than 1. So you can practice for a less than 1. So clearly I explained the amplitude scaling with respect to continuous time signal x of t. So at your home you have to practice amplitude scaling for discrete time signal x of n. Okay, like this you can practice. Okay, so this is the explanation, complete explanation about amplitude scaling. Okay, now we will move on to the next topic, that is nothing but time reversal. So now I will explain time reversal, the last one in operations on signals. So I will go now. We see time reversal operation. Time reversal. See, time reversal operation is the last one in operations on signals. So the last one in operations on signals is time reversal. Okay, time reversal operation. Simple. This time reversal operation is a special case of time scaling. So how can you represent time scaling operation on signal x of t? So the time scaling operation on signal x of t will be represented as x of at, time scale. That is, the scaling factor is with respect to t, that should be multiplied to the time t, x of at. If this a value equal to -1, then that condition we can call it as time reversal. Then we call the distance time reversal. Then the equation, if a equal to -1, what happens to that one? Then x of at will be equal to x of minus t. So this x of minus t is the time reversal of the signal. That is, with respect to time, it will be in reverse order. That is simply folding of the signal about the time origin t equal to 0. That is nothing but folding of the signal. So time reversal is also called as folding operation. The folding of the signal, okay, with respect to the time origin. That is, with respect to y-axis, about y-axis, if you fold the signal about the y-axis, then you get the time reversal operation. Or it can be also called as reflection. So reflection of the signal reflection of the signal about the y-axis, or reflection of the signal with respect to the time origin t equal to 0. The reflection of the signal with respect to the time origin t equal to 0. Okay, that means time reversal is also called as folding operation or reflection operation, or simply it is a mirror image. Simply it is a mirror image. Okay, simply it is a mirror image. Now simple, if there is signal x of t, there is signal x of t. Now I want to perform the time reversal operation, okay, on this x of t. Then it produces output y of t, which is nothing but x of minus t. That is, the time reversal operation on x of t can be represented as x of minus t. That is, the variable t is replaced with minus t. Simply the variable t is replaced with minus t. Simple logic. That variable t is replaced with minus t. Okay. Now I will explain this time reversal operation also with the help of a diagram. Small. Now I am considering the signal x of t. X of t as like this. See the same signal. 1, 2, 1, 2. So this is t and this is x of t. Now I need the time reversal of the signal. That is x of minus t. Okay. How can we get this x of minus t? Anyone? How can we get this x of minus t? Simple. So what are the conditions here? Write the conditions. What are the conditions here? For t less than 0, or simply x of t equal to 0 for t less than 0, and 2 for 0 less than or equal to t less than or equal to 2, and 0 for t greater than 2. This is the case for this one. Now here is time reversal. That is, the changes with respect to time. There will be no change with respect to amplitude. So how can I write y of t? Y of t equal to x of minus t. So which is equal to the amplitude of same. There is no change with respect to amplitude because we are performing the operation with respect to time. So that is 0 to 0. Now what is change? T. So in place of t we have to write minus t. That is minus t less than 0, 0 less than or equal to minus t less than or equal to 2, and t minus t greater than 2. Okay. So for this is the equation, if you think like that. Now, but I need these values for t only. How can I get? So if I divide the inequality by minus 1, then I can get t simply. So here remember one thing: if you divide or multiply the inequality by negative value, then you have to change the inequality. If it is greater than, bring it to less than. If it is less than, bring it to greater than. So whenever if we multiply or divide an inequality by negative value, the inequality symbol has to reverse. It has to change. It is a basic thing. Now if you divide this with minus 1, what happens? This will become as t. Less than will be greater than. 0 by minus 1. 0 by anything is 0. Next 0 by minus 1. Okay, nothing but 0. Then less than or equal to becomes greater than or equal to minus t by minus 1 t. Less than will become greater than or equal to 2 by minus 1 minus 2. Here minus t divided by minus 1, nothing but t. Greater than will become less than 2 by minus 1 minus 2. So remember this one. See now, so we have to go for this y of t with respect to this one. Draw this. So for t greater than 0, y of t equal to 0. That is x of minus t is 0 for t greater than 0. So there is no need of this one. Now we have to go for this one. So t greater than 0. T greater than y of t, 0, there is no signal. So if t is between 0 and minus 2, that is 0 is greater than t and t is less than minus 2. T is greater than minus 2. Okay. So let us consider this as minus 1, this as minus 2. Okay. Series. So this can be written as, how can we written? So t is greater than or equal to minus 2 means minus 2 is less than or equal to 2. So for this one, I can write like this. For this, minus 2 less than or equal to t less than or equal to 0. Okay. So between minus 2 and 0, the value is 2. Minus 2 and 0, the value is 2. The value is 2. Okay. Now, t less than minus 2. T less than minus 2 means minus 3, minus 4, whatever. The value is 0. So simply see, this is the given signal and this is the time reversal signal. That is, it is folded about the y-axis. That is, it is folded version, it is a folded about the time origin. That is t equal to 0, it is folded, hence it is called a folded signal. For the reflection or mirror image, you can say anything. Simply, it is nothing but folding the signal about the y-axis. So there is no need to do this every time. Simple. I will give a signal like this. You see a signal like this. So this is the signal. This is x of t and this is t and this is x of t. Now time reversal signal. The time reversal version of this one is simple mirror image. So this is x of minus t and this is t. So this is the mirror image of signal. So you can write anything. There is a signal like this. There is a signal like this. T, x of t, t, x of t. So what do you do? You have to write the x of minus t, x of minus t. See, simple logic. So reverse. This will go that side and that will come this side. Reverse operations. Okay, simple. T, x of t. Simple. If you think this as minus 1, this is 1, this is 2, then this will be 1, this will be minus 1 and this will be minus 2. So this is 1 and this is 2, this is also 1 and this is 2. Simple logic. Simple logic. So here also 0, 1, 2, 1, 2, 0, minus 1, minus 2, 1, 2. See, there is no change in amplitude, only there is reversed with respect to the y-axis. There is nothing but time reversal. So this is the explanation about time reversal. You can go for amplitude, you can go for amplitude reversal. So what is amplitude reversal? Simple. Amplitude reversal is nothing but the folding of the signal with respect to x-axis. With respect to x-axis. Simple. This is the signal. If you go for amplitude signal, for time reversal we have taken x of minus t. For amplitude reversal, we have to consider the signal y of t as minus x of t. So this is x of t. Minus x of t is 1 becomes minus 1, 2 becomes minus 2. So signal will be like this. The signal will be like this. Minus 1, minus 2, 1, 2. This is t and this is minus x of t. This is minus x of t. This is minus x of t. Simple logic. Okay. So for this, if I want to write the minus x of t, simply it will be like this. Okay. Minus 1, minus 2. So simply, there is the signal is folded with respect to x-axis. That is amplitude reversal. With this, we finished all the operations on signals. With this, I finished all the operations on signal. So I will give a brief summary on operations on signals. So this is the summary on the topic operations on signals. Summary on the topic operations on signals. First, a signal can be varied, in general signal can be varied with respect to two parameters, that is time and amplitude. Okay, amplitude. So here the operations of the signals will also be based on either time or amplitude. Okay, either time or amplitude. So based on the time, we have time scaling, time shifting, time reversal, time scaling, time shifting, time reversal. Okay, based on the amplitude, we have amplitude shifting, amplitude scaling, amplitude shifting, amplitude scaling, and finally we have amplitude reversal, addition, subtraction, multiplication. Okay, addition, subtraction, multiplication. First I explained addition, subtraction and multiplication with respect to the parameter amplitude in the top operations of signals. First I explained these three, and then I gone for time shifting. I explained you time shifting. So in time shifting we have two types. One is a right shift, and the one is left shift, positive shift, negative shift. That is right shift, and the one is left shift. Okay, that is we have delaying the signal or advancing the signal. That is recording time shifting. Next I gone for amplitude shifting. So in amplitude shifting there is upward shifting and downward shifting. I explained this. And next I gone for time scaling. So in time scaling we have time expansion and time compression. So in time scaling we have time expansion and time compression. And then I went for amplitude scaling. Okay, so in amplitude scaling we have amplification and attenuation. And after that I gone for time reversal. So in time reversal is special case of time scaling whenever the constant a value will be equal to -1. That is here x of t, the time reversal operation of x of t equal to x of minus t. And last I gone for amplitude reversal. So the amplitude reversal of a signal x of t will be equal to minus x of t. Okay, so this is about operations on signals. So first addition, subtraction, multiplication, and then time shifting, right shift and left shift, and then amplitude shifting, upward shift, downward shift, that is the amplitude shifting. And then I gone for time scaling, that is time expansion and time compression. After that amplitude scaling, amplification and attenuation, time reversal, that is x of t, the time reversal of x of t, x of minus t, and finally amplitude reversal. So x of t, the amplitude reversal of x of t is minus x of t. So this is the expression of operation of signals with respect to continuous time signal x of t. And I had given you the work to practice the all operations on signals with respect to the discrete time variable. Okay, I hope you will practice the operations on signals with respect to discrete time signal, that is x of n. So you have to do all these operations, all this time scaling, time shifting, amplitude scaling, amplitude shifting, time reversal, everything with respect to discrete time signal x of n, with respect to x of n. That is your work. So with this I am finishing operations on signals. Okay, the topic operations of signals is completed. Okay, thank you one and all.